You're listening to the Knowledge Archives podcast. Welcome to the Knowledge Archives podcast. We're a group of students on a mission to learn from as many different disciplines of knowledge as possible. I'm your host, Madhav Malhotra, and today I'm pleased to be joined by Dr. Daniele Cocco, a staff scientist at the Lawrence Berkeley National Laboratory in the US. His research focuses on X-ray optics, a very specialized aspect of optics and physics in general. Technology to manipulate X-rays is found in a very large number of applications in modern industries. So thank you for joining me today. I really appreciate you taking the time, and I'm very excited to learn about this specialized area of physics. I thought, first of all, it would just be great to hear a little bit about who you are and some of your past work and research interests.
Thank you for having me here. I'm Daniele Cocco. I'm coming from Italy. I graduated in the University of Trieste in 1992, a lot of years ago. And I worked there for 90 years, always related with X-ray science, X-ray optics. And later on, 2011, I decided to move to the US and I joined Stanford University, where they were building the upgraded of a free electron laser that is a machine for study ultrafast phenomena. And it was exciting 8.5 years. And then I moved to Berkeley a little bit more than 1 year ago. That actually was my dream since when I was an undergraduate student. So yeah, finally I'm here. I'm still working on X-ray optics, X-ray science. And I'm very happy to be with you today and tell something about this science that is not very popular around the world. It's a niche area, but there's a lot of cool stuff in.
And I think, first of all, it really makes sense to talk about the basics of what X-ray optics are. I know that I didn't know much about this before I looked into it. So let's just start off by establishing like a few basics. Please just correct me if anything I'm saying is incorrect or if you'd like to add anything to the basics that I bring up. So first of all, optics in physics is just a branch of physics that deals with the behavior and properties of light, and that includes how light interacts with matter. And that part is very key when it comes to X-rays because unlike the, say, visible optics that most people would be familiar with from high school physics, X-rays are very different in terms of how they interact with matter because of how they're very unlikely to refract or reflect off of most substances. Is that correct?
It is correct.
All
It
right.
is mostly to do with the wavelength that becomes shorter and shorter.
Mhm.
The visible light, you may know, it's a wavelength that is something like 600 to 400 nanometer. And the X-ray goes down to 1 nanometer. And just to give you the scale, one atom is something like 0.3, 0.4 nanometer. So when our wavelength is very short, it's difficult to really interact with the atoms. And so, yeah, you are perfectly right. It's very difficult to handle the X-ray.
But that being said, this is still a very, very important topic, X-ray optics in general, because of the wide variety of applications that it's used in, which I don't think most people would be familiar with. But if we look at applications, especially in imaging, which I thought was very interesting, because X-rays don't interact with matter or reflect off of matter or refract from it as easily, we can do a lot of very interesting things where we send X-rays through matter and collect some data as they pass through it. So for instance, with X-ray imaging, we can do this in hospitals where if we send X-rays through a person's body, in some parts of the body, like with bone, the amount of change that the X-ray has as it goes through the body with respect to its amplitude, it's different in, say, bone versus, say, just regular skin tissue. But because of that, we can take a sensor at the other end and look at the contrast between areas where the intensity has changed a lot, the amplitude, and where it has changed a little bit. And that allows us to create images with the typical X-ray scanners in the hospitals. But then also, we can look at other properties of the light wave. For instance, with changes in phase, we can have another type of imaging with phase contrast imaging. With microscopes, we can use X-rays as a specific technique to make very interesting images, but then also all the way up to telescopes where X-ray based telescopes can peer further into space than a bunch of the other types of light waves that we are collecting. Is that correct?
Is it correct? You mentioned three of the main topics for sure. And you actually mentioned two important words, phase contrast and amplitude. That was great. Actually, the best way now of imaging the tissue of a person is doing phase contrast, in which you really work with this tiny different absorption that is in one kind of tissue with respect to another. And if you have a good detector, you can really detect incredibly small detail with very high accuracy. You may have skipped one topic that is actually what I want to, that is the X-ray used to probe the matter, but maybe we can discuss this later, is a fourth kind of field of study that is based on what you just mentioned, but it's a little bit different, in which you irradiate a sample, a drug, virus with X-ray, and try to understand how it behaves, measuring the interaction between the X-ray and the virus.
Mm-hmm. Do those have to do anything with other types of applications where you have X-ray crystallography or X-ray fluorescence, where the X-rays, when they go near, say, some kind of atom structure, they might change direction a little bit as they get deflected off of electrons, or when they actually hit atoms, well, they might release other X-rays aside from the one being shown at them, and then we can use those to measure properties?
That's correct. Yes, exactly. So diffraction is the most used method to characterize a pharmaceutical compound, a virus, a crystal, and so on. The problem is that you need to freeze the sample to measure with X-ray diffraction. You want to have the sample fixed, frozen, then you send the X-ray and measure the tiny deviation from the reflection beam, and this is the diffraction. There are new machines like the one I was working in which they don't need to freeze the sample because they send so many X-rays at the same time that they can have an image right away in a single shot in 1 femtosecond, that is something like 1 million of a billionth of a second. And so you can reconstruct the image with whatever you want to measure in vivo, in its natural ambient. And that is very good. Fluorescence and other techniques are mostly used for solid sample, so surface science or big crystal, but they are also very, very powerful, and they have been used mostly for studying things like environmental issue, like how can we dissociate CO in CO2 or NOx that are pollutant in nitrogen and oxygen, nitrogen and water, and all these chemical processes are studied with the technique that you just mentioned.
Mm-hmm. And it just goes to show how, even though, like myself, a bunch of people don't know about how different X-rays are from visible light, all of these really, really important applications show how studying them is just so crucial in so many of our modern electronics, modern systems, modern sensors, etc. And hopefully for people who haven't heard about this topic, that serves as a good beginning. So just to recap, X-rays have different properties that allow them to pass through matter, and the changes that happen to them, the minute changes that we can measure as they pass through matter, let us do very, very interesting things, especially with the applications that we just discussed. And this is where your research comes in, where, because X-rays are so difficult to manipulate and they often do not interact with matter, it's really hard to get them to, say, go where you want, get them to be used in the ways you want, because you can't just use ordinary, say, mirrors or lenses with them like you could with visible light. Could you explain a little bit about the challenges that come with the instrumentation that we use when working with X-rays and your work there in particular?
Yeah, okay, you mentioned that they don't interact with the atoms. And of course, it's a high-level assumption. In reality, they do. But the point is, as I was mentioned before, since the wavelength is so small, let's say the X-ray at a wavelength of 0.1 nanometer, and the atom are separated by 3 nanometer, the chance that they don't hit the atom is high. But imagine that if instead of going in normal incidence, so you see the atom from the top, you go grazing, then this 3 or 10 atom separation between the atoms 10 nanometers separation between the atom becomes 1, 0, 5, 0, 1. Let me one step back. This is a very naive explanation, okay? In reality, the things are much more complicated. This has a quantum wave that interact with probability and so on and so forth. But just to give an idea, imagine when you go grazing enough, you actually see the atom, and so you can be reflected. So when we deal with X-ray, let's say from soft X-ray to hard X-ray, so from everything above the UV in terms of energy, you need to go grazing. So yes, normal incidence mirror doesn't work. You need to go grazing, but really grazing. In the hard X-ray, you need to go to much less than 1 degree. So for doing this, your mirrors become incredibly long. I deal with mirrors that are up to 1.5 meter long, but there is another problem. Let's do this. Imagine to see the planet Earth from an airplane or from the space, and you see a hill. You don't see the hill, you see flat. And this is a normal incidence mirror. Now, if you are on the ground, this 300 meter or 1,000 feet high hill, it's huge. I mean, you look up and you see the hill. And this is what the X-rays see when they go very grazing. So every small defect on the mirror will destroy your wavefront. If you want to do coherent imaging, like the one that you mentioned before, when you want to really see the contrast and your mirror is bad, you just don't see anything. You see just a diffuse beam that you don't know what it means. So the mirror are incredibly perfect. Perfect at a level of 1 nanometer over 1 meter. Just to give you the scale, 1 nanometer over 1 meter mirror means that you draw a line all around the planet Earth, and you draw so perfectly that the maximum deviation from the ideal line is less than a pencil. So this is what it means, how precise our mirror has to be done. And to do this, there are actually techniques that in the past, it was just computer polishing. So you have something like when you clean table or whatever, something like that, rubbing and try to make it flat. All the telescopes were all made like this. You have wonderful science with that, but not the one you want to do today. Today, we are really going to remove atom by atom from the mirror. This means incredibly precise control of the temperature, the position, everything. And that's its stuff. And then you have to measure, be sure you can measure that properly. There is all a technique to that. Metrology of optics involve laser beam that interact on the surface, are reflected back. You measure the difference in angle with a precision of nanoradians. That means 1 million of 1 billionth of normal degree angle. So you divide the normal degree angle, the 90-degree angle by 1 billion, and you go to the nanoradian level. So this is the kind of precision we need. And again, control of the environment is paramount in everything. And on top of that, you said everything absorbs the visible light, but the gas can absorb the soft X-ray, some hard X-ray, and can diffuse the beam. So again, all our instrumentation needs to be in ultra high vacuum. So we have big pumps that have to create a vacuum that is more vacuum than the vacuum that is in the space, just to prevent the beam to be diffused. So this is more or less the basic problem we have. And then we can go into the fact that the small amount of radiation that is absorbed is still depositing some power. If you illuminate with a lamp a mirror, you don't see it deforming, okay? The mirror stays as it is. But at the nanometer level, that mirror becomes like rubber. So you really deform with just the light, you can deform the mirror. So we need really to control the temperature very precisely. So often we go to cryo cooling, so liquid nitrogen, to keep our optics stable where they are. It's a fun job, but it's a lot of challenges.
Yes, I can imagine. But I just want to make sure that I'm understanding this correctly. So when it comes to an X-ray, manipulating it in the way that it diffracts off of an atom, it can't directly hit an atom. We need it to just graze by the atom as it goes past it. Very exactly. Is that correct?
Well, the light is actually a wave. So what's happened is that there is an interaction between the light wave and the lattice or whatever the space. It doesn't need to be a lattice, just matter. So the wave stay on top of the mirror and oscillate on top of the mirror. And in this oscillation, you can have absorption, like in some visible Like, for instance, why the gold is gold, because all the other wavelengths are absorbed. So if you have absorption, well, you're lost. You don't have any reflected beam. But if you have an angle and a material that will not absorb that particular wavelength, then it is reflected back. It's the idea of thinking about reflected by the atom is wrong. But it was a way of saying you need to go grazing enough to give some substance to your material to permit this wave to be generated and reflected or diffracted.
So the wave is going up across this mirror that's down to the level of all of these micro levels of just the individual atoms and aberrations in the mirror. It has to be very perfect, has to be very long, and the angle between the X-ray going in and the mirror has to be very, very small, such that the wave actually reflects off.
Correct. Yes.
Okay. And then with all of the complexities on top of that, as you mentioned, with the controls you have to keep for environmental conditions and not having gases interfere, this is very, very interesting. May I ask, when we're trying to design these kinds of instruments, usually when you think of X-rays being used, you think of the X-ray scanners in hospitals, and it's hard to imagine a 1.5 meter long mirror being used there. What kind of applications are you designing these instruments for at the lab right now?
Yeah, okay. Let me say one thing. The scanner in the hospital are usually made with an electron gun hitting a target, and there is a crystal deflecting all the X-ray, focusing all the X-ray on your sample. So it's much simple. And in particular, they use wavelengths that are short enough to travel in the air. And they don't care much if there is absorption or diffusion, because they are not going to measure nanometer level or micron level. So that is perfectly suitable for the hospital. What we want to do instead is going to measure the atom, the chemical process, the biological process at the level they are happening. So they don't happen at the level of 1 millimeter. They happen at the level of nanometers. 100 nanometers, sub-micron, micron maximum, or something like that. So your light has to be concentrated on this small dimension and has to be uniform and stable over that dimension for most of the applications. There are applications that can give a lot of important results that just need some light, fine. More advanced, you really need to be able to focus all this radiation in a small spot. For instance, what I was mentioning before is when you go to measure the interaction between a pharmaceutical compound and a virus. You want to do that in their environment. So you need to have a spot that has more or less that dimension with all the photons there. And this amount of photons is unbelievable. Imagine to take all the light that is sent by the sun to the earth, all that, and focus them on a golf ball. That is the quantity of energy density that we deliver at the sample. So there's no material in the world that can survive that, okay? So we destroy everything with that machine. It's not for military purpose because you are in vacuum, you have 1 kilometer machine to produce that, so it's not a weapon. But we are a completely different world with respect to what you can have in X-ray optics in general. We are really dealing with something that is order of magnitude more precise and more accurate than everything else that you can find around.
Mm-hmm. Yes, it goes to show the enormous differences between this field and the other conventional branches of physics and engineering that people are used to. But it also goes to show all of the limitations that we've been talking about, all of the little things that need to go exactly right if you want to get the experiments to work right, get the applications to work right. One interesting limitation that I was thinking about that we haven't talked about so far is cost. So you've been talking about how the technology has been growing ever more precise and sensitive, and that's amazing. Could we also talk about the current limitations with cost and how that has changed with this technology over time?
The costs are very high. This instrument costs a lot of money. The research to build this instrument years long, and in general, okay, full disclosure, a mirror that we use to focus can cost up to $250,000, a single mirror, with all the older around bender to make the perfect focus and so on. Maybe a little bit less, but the costs are incredibly high. And this is the reason why there are not very many laboratories in the world using X-ray. But the research behind that is also very expensive. We are, for instance, now at the OE funded project just for the cooling of the optics with cryogenic, with liquid nitrogen. I know NASA is investing a lot of money in X-ray because, for the reason you said before, the X-ray are not interacting with the matter. So they are trying to go to where this was a sentence probably for Star Trek, where nobody have been before or something like that. They want to go to measure the deep galaxy by being able to detect the very old X-ray, the X-ray with the wavelength so short that it's well below 1 amp, but well below 1,000 times less than what I said before. And to do that, they are developing mirrors able to reflect that kind of light. And this is a multi-million project that is going on, and hopefully they will succeed in doing that.
Mm-hmm.
But yeah, these things cost a lot of money.
And has this been changing over time? Because I know you were talking about earlier a bunch of the mirrors that we were using in earlier days that you mentioned you were just sanding them down. Those definitely wouldn't be as accurate, but did they cost less than that, or was it still like it was always the nascency of this technology, always the new things that were being developed at the edge of this field that have kept costs high for most of the very intricate instruments we're using today?
No, there's been an evolution in science in general. It's no longer the romantic science that was in the beginning of last century, in which one or two scientists alone could have built a wonderful machine and have a Nobel Prize. In Berkeley, where we are, we had still the cyclotron that has been built, wonderful, beautiful. Now, things changed. So X-ray optics, in my field, was a byproduct of the nuclear reaction machine when they see how better the machine designed to study nuclear interaction. And they have seen that there was some radiation that they would say, this is destroying our experiment. They want to get rid of this radiation. But then someone realized that actually this radiation is cool. We can do a lot of things with that. And they start to use hand polish mirror just to take it out and bring to a sample. And so techniques were invented to measure the matter with the X-ray. And this is when people realized, wait, we can do really a lot of things. And slowly there was this virtuous loop in which people with nothing start to have some result. So they want to have better results. So they build better machine, they build better optics, and they have better result, and so on forever. And the things are going on since 1960 in this way with some big step. The last big step has been something like 10 years ago when we have developed the free electron laser, ultra short pulses. So that is when we went to sub-nanometer optics and when the cost went up a lot. Since the 90s, the costs were high. That's true, but it's when the virtuous loop that I mentioned before, it started to be really gain the attraction of big shot scientists around the world. And they realize that there is a lot of things you can do with X-ray. And so government agency, private foundation, and so on start investing money in machine, X-ray optics, and experiment. And this is when the things start to be really very complex, very complicated. It's technique. People who does that for job for their entire life, just to be able to measure the X-ray optics. Laboratory dedicated only to measure mirrors for X-ray optics. So it's an evolution of the science, like most of the science of physics around the world, yes.
Mm-hmm. And this gets into another question I had about new developments that are currently going on in the field. You talked about the increases in precision, you talked about creating ways to control noise from the environment, and also, again, the increases in power, etc. Are there any other developments when it comes to addressing the problems you outlined with all of the limitations we were talking about earlier?
Yeah, as much as we have done a lot of progress in the last 20 years, we still have several issues in performing the experiment as we want. One of these is for lithography, in which they want to have a smaller feature in the chips to make the mass storage device as small as possible. They are now using coating for mirrors that let they use 13.5 nanometer wavelength. So your minimum cell in a chip is of the order of 13.5 nanometer. There is a study to try to have this mirror working at 6 nanometer or maybe 2 nanometer. And so you can reduce of a factor 10 squares, so 100, the dimension of the storage device. But we are not yet there. The other thing is experiment. The experiment, once you have something good, you want to do this better. So there are experiments that was not even conceivable years ago. And now we start to think maybe they are feasible, but in which you need the control of the position and on the shape and on the energy of the wavelength perfectly. So what is coming up here is something I'm not a big fan of, but I know will be the future, is the machine learning and diagnostic that instead I'm a big fan of. So we are trying to implement as many and invent new diagnostic to be able to measure real time the light without interacting with the light that goes to the sample. So some side band light or something from that. And with machine learning tool, being able to predict if there is any kind of drift or variation of the light. That is a long shot. It will not happen in the next year. Probably will happen in the next 5 years, but it's happening. This is when we will be really able to control at best. And then maybe some scientists will come out with some new things to measure, and we have to start over again.
Yes, I think that's really interesting to hear about, especially when this major technology with machine learning being applied in so many disciplines gets to interact with this very specialized but very useful technology. And this gets into the last question I had for you, which was about the gaps in research still in the industry. So what are the, say, biggest questions that we're still trying to answer?
Good, yeah. Actually, well, the theory of the interaction of the light with the matter is back in the beginning of the last century. So it's something people knows, but how to use it is actually something that is still can be improved. Let me say in this way, otherwise my scientist fellow can become mad. So there is still improvement to do that. So the point is, we have some physical limit. That is the following. If you send too many X-rays to a sample, you destroy it. If you send it too few, you may not have the information you want. So we are still at the level in which we are trying to figure out how can we perfectly confine the experiment such way we send the right amount of photon to have the information we want without damaging the optics and mostly without violating any physical principle. For instance, if the wavelength has 2 nanometer, you cannot see anything below 2 nanometer. So the idea is to try really to understand how can we study some sample that are so fragile, so delicate that it's not compatible with the radiation. One of the things that I mentioned before are this new ultra-fast machine in which you irradiate the sample with so many photons that you destroy the sample, but you have the image of the sample before destroying. So you do really a mass destruction there. You destroy millions of samples to collect your entire image, but you can do that. And this technique is still in evolution because the machine is not yet there. We don't have yet machine able to perform at the level we want, at the repetition rate we want, but we are going close to that. And then there are some other things that are on the horizon that I would really like to see coming, but it's really embryonal and I don't know when it comes. If you select the proper wavelength and you focus in the proper position, maybe inside the body of a person, you can target a particular cell, easy to say, a cancer cell. If you target that, you can let the rest of the body untouched or unaltered and just focus on that part inside because you are using the exact wavelength that interact with that particular part of the body. We are far away from that. But that is something that really can give some more than useful, life-changing use of the X-ray. In general, surgery with the X-ray I think it will become something for the near future. For material science, the optics is just giving more and more precise and accurate data. I don't see a big leap. I see small improvement to go better and better, to try to see something that was not visible before, something in which we will discover it today and someone will see the benefit in 10 years, maybe. So it's not something that, oh, we discovered a new something. Probably not. I don't see this happening soon. I see happening a small improvement in the knowledge that slowly will provide something better.
I think that's really interesting, and it's very exciting to think about for the next generations of scientists, how they might be able to build on top of this knowledge to derive new insights, even though it might not be clear to us now. A lot of things in science are like that, where it wasn't immediately obvious what the use was, but then here we are with all of these amazing technologies that came from this very, very specialized field to begin with. So the last question I wanted to ask you, usually I end off the podcast by asking the researchers where people may be able to learn more about the field or their work. But then again, this is such a specialized field, and as we were talking about, there's not a lot of places that have a bunch of information about this. So I was hoping to ask you, do you think that there's a large gap in knowledge for people in other disciplines or even other aspects of physics to learn about this topic? And do you think that kind of holds back the amount of research being done here, where, say, a biologist or a surgeon might see an application that a physicist might not immediately see, but because the area is so specialized, we haven't been able to unlock those connections?
The last one is actually a very important topic because we are seeing there is some big conference like SPIE with, unfortunately this year will be not because of the COVID, but where there are different disciplines. And if you go to some section that is not related to you in particular, you see that they are trying to develop something you have developed 10 years ago or vice versa. And that was for the wavefront sensor, and that is for astronomy or for even synchrotron on a one generation to another. So for some reason, despite the fact that we are publishing so many articles every year, people are still closing their work. Not everybody, okay, but in general, as you are trying to see what's happening in your field rather than in a field without. That's why, something like 20 years, we have tried to join the astronomy community with the surface science community. Come out that 90% of the things we do are similar, but we were using different fonts to try to solve very similar problems. And so the same is very likely valid for a lot of other science. Again, it's very, very topical, this research, but a lot of things that has been developed, like, I don't know, piezo actuator for moving optics quickly, for laser or for X-ray, that is something that is usable in a lot of other contexts. And the study has been really separated. There has not been synergic between the various fields. So it's both fault. It's our fault. It's everybody else's fault in a sense. We should be able to know what the other people are doing better. The problem is that this field, even if it's evolving not at the speed of light, but it's evolving. You need to be focused on your field because it's a lot of things that is going on. So if you start to disperse yourself too much, you may lose the track of your research. It's good that there is often this synergic. It should be nice to have more of this synergic workshop in which you try to merge people of different world and try to understand if they help each other. And of course, then there is the private industry. Then they don't want to. They want to just have information, but they don't want to give. So that's a little bit more complicated to work with. But we are happy to provide information also to them. And if you are interested, the Berkeley Lab, LBNL, has a site that is managed by the Center of X-ray Optics. So you can Google CXRO, and you found it. That's a beautiful small website where you can find a lot of information of X-ray optics technology, how it and that is not necessarily up to date, but that's all the basic you need. And from there, you can go to other basic if anybody is interested in knowing more about X-ray optics.
Well, that's great to hear, and I really appreciate you providing that information. And I'm sure if people are more curious about this could be a very interesting adventure to go on and learn more about this very incredibly specialized but useful field. And again, I just wanted to thank you for taking the time today and explaining so much of, I know it's just the basics for you, but for everyone else, it must be so mind-boggling to hear about all of these amazing details that never get talked about outside of the X-ray optics community. So thank you.
My pleasure.